All right, these guys are worried about running out of time, so we're just going to start about 20 seconds early. Our next talk is Voight Kampffing The BlackBerry PlayBook. I'll let these guys explain the Blade Runner reference later. We have Zach Lanier, who works with me at Veracode. Try not to hold that against him. We have Nell, who works for Intrepidus Group. And I was noticing in reading their bios that they both like cats, and they were both also very intrigued by the laser pointer a minute ago, which also makes them act like cats. So anyway, give it up for Zach and Ben.
All right, thanks. So, like Chris said, Voight Kampffing The BlackBerry PlayBook. This is our introduction slide, as you see here. I am Edward James Olmos, and Ben is, I forget this actor's name. Anyway, I'm a security researcher with Veracode.
I'm a consultant with Intrepidus Group.
Now we have to pass this mic back and forth. So why does our talk matter? Well, for us, it was the Playbook is a new and different platform, and something we hadn't really looked at before, and only a few other people had actually looked at. The pitch, right, and for the RIM people in the audience, correct me if I'm wrong. One of the things that it was to target was enterprises, right, like an enterprise-friendly tablet. And that's what we thought was pretty intriguing about it. And one of the big features was separation or containerization, right, of personal data, so you could use it as a consumer device, and your corporate or enterprise data. So we like to say that we could steal that corporate data. Did that flame in as it was supposed to? Awesome. So, or at least we used to be able to anyway. So our agenda, we want to talk a little bit about the platform and all of its underlying workings as much as we can in a short period of time. Go over apps, runtimes, stuff like that. Talk a little bit about our methodology, what we did to kind of tear this apart, and what findings came out of that. And then just a few additional areas of consideration for those who are curious and want to continue researching this, or areas that we in the future might take a look at. So a brief deviation, in case you were wondering where the name for our talk came from, and two of you were. Harrison Ford was in a movie called Blade Runner based on Do Androids Dream of Electric Sheep. He plays a character named Deckard. Deckard hunts replicants. Replicants are androids, right? So the code name for the playbook was Deckard. So he's an android killer. So the playbook is the android killer. Voight Kampff machines were the machines that were used to interrogate replicants. So hence our theme, we were interrogating Deckard, who may or may not be a replicant himself. Anyway, whatever, thought it was funny. So a little bit about the platform. The playbook itself is built on TI's OMAP 4430 system on chip, which is the core of which is it's a dual core ARM Cortex A9. So cool ARM stuff applies here. The tablet OS, the operating system on it, is based on QNX Neutrino 6.6. So a lot of the 6.5 stuff is applicable to 6.6. So all the developer docs. RIM had acquired QNX a few years ago, and eventually moved this to being the foundation for tablet OS. Notable components include WebKit for all of the web UI rendering stuff. So, if you have opinions of WebKit, they apply here. Adobe Flash, it's a Flash-enabled WebKit browser, so more opinions apply here. Adobe Air for one of the app runtimes, so a lot of the apps are actually written in for Air. This other component called BlackBerry Bridge, the thing that allows you to pair your corporate BlackBerry handset with your tablet and access all of your contacts, email, calendar, any of the things that you're used to on your BlackBerry handset. So a use case there would be you have your corporate handset and your enterprise or your consumer tablet, and you can now work with your corporate email through your tablet. So this will be a little important later. So a little bit about QNX. It's a microkernel architecture, so pretty much everything that you would normally have in like a monolithic kernel, like Linux, networking stack, I/O, process management, human and machine interaction stuff is all in the kernel. And QNX, everything is implemented as a service outside of the microkernel itself. So if you were to remove like the networking component or kill that service, as you might call it, there's no such thing as like IP stack anymore. Like the networking just goes away. There's a trusted boot process, so all the firmware updates and everything are signed. As each service is supposed to come up, it's supposed to be verified, and the microkernel itself is really only the trusted, the God process and everything. QNX 6.5 up until, or QNX 6.5 and below didn't have things like ASLR, didn't really have a lot of memory protections or exploit mitigations on it. I think QNX or RIM had hired a few people. I like to think Ollie Whitehouse had something to do with this, but I might be wrong, just based on some of his research about ASLR. QNX 6.6 introduced ASLR, so you know, that's something to consider. I'm going to try to speed through some of this. Dingleberry, an honorable mention. This was the first public privilege escalation, root privilege escalation for the playbook. It was discovered by a guy named XPVQS and another guy named Neurolic, and Chris Wade or CMW.me packaged it into a nice point-and-click interface. The too long didn't read version was the backup blobs that come out of Desktop Manager aren't signed, so what they did was did a backup of the system, changed some of the contents of the backup blob, restored and overwrote a config file for Samba that would execute a shell script as root or a command as root, and that's basically the end result of getting root. It's now irrelevant for a couple of reasons. That issue's been fixed, and also Chris Wade, the guy who packaged all this, said he's not supporting his exploit anymore. So for whatever that's worth. A few other notable security controls. OpenBSD PF is available on tablet OS. It's used for locking down network access for certain services on the playbook, so apps can't talk to them. POSIX ACLs on the file system. We'll see why this is relevant, but that locks down you know, a lot of file system objects. There are, for all the native binaries and native apps, if you're developing third-party apps, they all have your standard compiler and linker protections, ProPolice, there's stack canaries, position-independent executables. They do full railrow for all of the native binaries on the system, as well as those are the default values for when you're doing native app development. And like I said before, ASLR is in effect for all of these. All right, so quickly, PPS, persistent publish subscribe. It's a file system-based eventing and data sharing, or kind of like message passing system. It's really simple but pretty elegant, and it's a simple design. If you're used to like IPC stuff, you know, you pass messages through semaphores or whatever. This is just a way to like write out to a file and have it be read back into something else. But it adds a few other additional features. So the example we give here is monitoring network interface state. So everything exists under this PPS directory or /PPS. So here we have, I'm just running cat /PPS/services/networking/.all, and I pass in like these weird, almost URL-like parameters, right? Question mark, wait, comma, delta, comma, F equals Wi-Fi connected. So what this is just saying is it actually causes cat to just wait for more data to be to get written into this file, and it rebuffers it. And it's almost like running tail on this file, except you get the full contents of the file the next time it's updated rather than just the new lines. Delta will only show the changes to that file rather than the full contents of the file each time. And then F is just a filter. So what we're saying is only when this property in that file gets updated, Wi-Fi_connected, do we see that change reflected in cat's output. So here we have like Wi-Fi connected, Boolean false. Then when I flip the Wi-Fi adapter on, that property got updated. Now it's the Boolean of true. So whatever, like super simple file system based eventing mechanism. Some services that are on here. There's this thing called Authman. It maps app permission, so you know the access Bluetooth permission, for instance, back to the corresponding system resource that will need to be accessed by the application. And it does this by setting file system permissions on various PPS files, by adding in PF rules if it's something network related. A lot of this underneath is just a bunch of Python and shell script glue. So if you're curious, that's potential for issues there. If you wanted to go look, I hope that's readable. In /etc/authman, all the configuration files for what authman needs to do when an app wants a certain permission. It's these two files, filename.res and filename.acl, each named for a different profile type. So some of the examples we have here are carrier.acl, carrier.res, corp.acl, corp.res. And the carrier.acl thing piqued our interest because when the playbook came out, it wasn't on a carrier. There was no cell radio. It was just Wi-Fi and Bluetooth. But anyway, there's also this special thing on Qnix called a resource manager dispatch path. I kind of likened it to just a pipe or like a FIFO or something. It turns out that when an app gets launched, the launcher process probably, or we speculate that it sends messages into this /dev/authman pipe, and authman then takes some actions to set up stuff for the app, like the appropriate group memberships that it needs at runtime. So that was something we learned today. Here's an example of some of the things authman needs to do when an app wants a certain permission. So for instance, we have here use camera prompt a wildcard, but allow sys.wildcard. So what this is saying, for any app that's not in the system category, if it wants to use the camera, the user will get prompted, and authman will know to give the user like the dialog, do you want to allow access to the camera? Read geolocation, access shared, access sys, manage certificates. You'll see manage certificates, for instance, denies everything, but explicitly allows the browser to manage the certificate store. So it also sets the appropriate ACLs on file system objects, like I said. So down here, we'll take the use camera permission again. What actually happens underneath is authman will set a POSIX ACL of read-write on /pps/services/multimedia/camera/control for the app that's being given that permission. So that app's UID will now have an explicit POSIX ACL entry to be able to read and write that PPS object. Read geolocation, it gets the ability to read and write the geolocation control PPS object, so forth and so on. So there's a zoom on that thing. So that's I hope you all kind of get what POSIX ACLs are like, right? Just extended, it's Unix permissions, just a longer list of them for explicit user IDs and group IDs. Like I said before, authman also deals with setting up PF rules. So what it'll do is if an app needs to, if an app needed to access like a particular service, listening locally or listening somewhere out on the internet, and there was a corresponding app permission for that, the UID for that app would get or GID for that app would get a rule in PF that allowed it to talk to that IP or that remote host. More importantly, what this does is limits access for apps of certain group IDs from accessing Sapphire Proxy, which is a service that listens locally to facilitate that BlackBerry bridge we mentioned earlier. So just kind of file that away in your head for later as to that word Sapphire Proxy, because it'll be significant. But just know that right now these PF rules basically allow any of these GIDs like 900 through 909 and anything above 9999 from accessing 127.0.0.2, where some of these Sapphire Proxy services listen.
Hello. So we're going to talk a little bit about the application model on this platform, like how you build and deploy apps and what that kind of means. So playbook applications, similar to Android's got APK files, et cetera, et cetera. So the BlackBerry application package, it is like a jar, but it's packaged by a BlackBerry service, so it's called a bar. It's a bar file, but it's essentially a jar. It's all the same structures. It contains a file. It's got an entry point that basically says which thing do I run. and it can basically like a bar file can be a packaged Air application, like Adobe Air application, ELF binary. With the latest release, you can run Android applications, and I believe Python applications as well. Just a little bit more native applications. Essentially, like if your app is like defined as like a native application, you can do different things like actually run like shell scripts. Like you're not limited to just running ELF binaries. As a part of that setup process, you can set like environment variables and things like that. The Air applications as well can actually also interface with compiled libraries, which is kind of interesting. Just some real quick permission stuff. Basically, like if you would go to RIM's website and the like the developer docs for PlayBook, there's not a lot of documented permissions. When I built this slide, there was like eight permissions. But if you actually go in and like if you saw the slide where Zach kind of like showed you how those permissions are built out and like lists what they are, you know, we kind of like looked through and saw like you can't even read this, but there's like 48 permissions at the time. So there may be more at this point. Point being there's just basically like a lot of things that as a developer you may not realize is an interface. Interesting side note, Adobe Reader is like, we looked at a lot of PlayBook applications and basically Adobe Reader uses a couple of like interesting permissions that nothing else was using. It had this permission called perimeter_corp, and basically it's you can kind of see like along the bottom here, perimeter corp. It's got specific permission for Adobe Reader, and I believe what that is permission to access things that are, we talk kind of how like the personal versus enterprise data. As I understand it, which it may be incorrect, this is basically like giving Adobe Reader access to like this like corporate information. Like you get an email and you're, from your Bez and like you want to read it. Like it's
it'd be saved off in this container called a perimeter.
Yeah.
It would be able to access the files from path that had whatever that PDF was in that corporate that perimeter corp container.
Right. Anyway, it's just interesting that Adobe Reader has got these specific permissions.
And also run here native as well.
Yeah, that's another thing. It is an Air application actually. Adobe Reader is an Air application, but it runs native code. So that's interesting. Just a little bit about our methodology, what we used to kind of like get into this platform. It was new. There wasn't really like any documentation or anything, so we kind of had to build our own processes. There's a mode called development mode. Basically, if you're a developer and you want to deploy applications, you basically like put this thing into developer mode, and then you can use like some SDK tools to sideload applications, gain like limited shell access. This development mode, you can see, you might be able to see, there's actually like an expiration date. So like if you put it into dev mode, it's not like some security risk like forever. Anyways, developer mode, it basically, when you put it in developer mode, it basically exposes a CGI. The platform actually runs a web server. And through this app installer.cgi, you can do different things like install and launch applications, enumerate applications, terminate apps that are running. Just from the command line, you can see a few options there. I'm not going to run through it, but list installed apps, is the app running, et cetera, et cetera.
So that BlackBerry deploy command actually interfaces. That BlackBerry deploy command will actually connect to that web server once you've connected it. Once you've authenticated to the PlayBook using BlackBerry Connect, then you can use BlackBerry Deploy, and it'll just use this it'll authenticate again to the web server and allow you to push bar files and remove bar files and everything. So
There's another service called QCondor, which is pretty interesting. You know, from a security perspective, basically this QCondor is a service that, you know, spins up an SSH server, and you can SSH into the device. We looked at this pretty closely to see if there's like some way that we could, you know, do some like file system tricks to kind of like load something other than like an unprivileged, you know, make this like unprivileged shell available. But it's actually like hard-coded to, you know, only allow this like dev user account that's like in the binary itself. But it's there. It's interesting.
And, when you run BlackBerry Connect and authenticate it, it actually uploads your SSH public key, and that's why if you go back real quick, it disables password authentication. It spins it up. It passes an argument of only allowing the dev user at the as an argument to SSHD. So even if you did like somehow symlink like an overwrote roots, you know, authorized keys file or something, you technically still shouldn't be able to. At least we weren't, and I'm sure someone knows more SSH tricks than we do. But dev user would still only be the user allowed to log in.
So just like some other notes on like what we use to explore the system, kind of. There's actually a QNX software development platform. They call it SDP, which is basically like you know, a virtual machine, like a VMware virtual machine, that gives you access to like a lot of like native QNX tools. The playbook simulator is kind of like the same thing, like the, you know, RIM distributes this playbook simulator. It's the same thing as the SDP, except it's like got the you know, like the playbook user interface. You know, the tools are all stripped out. There's tons of QNX documentation, user forums, and you know, software development manuals and things like that. We were able to, you know, kind of dig into the firmware images a little bit. There's an SDK for deploying software, obviously, and there's actually like, you know, the source used to be open, not open source, but available for QNX, and there are still some source code repos on the internet hosting that. So some research findings. The first thing that we really looked at was system updates, and it's basically, you know, the actual process itself is pretty bulletproof. It uses signed packages, like the package itself, like all BlackBerry or like all Playbook applications, is signed, and then different components of the firmware image itself are signed. And it's basically a three-stage process. You pull for updates. You know, you get back a list of what updates are available. You request an update, and then you get like a list of packages associated with that. And then you can download the individual packages and install them. And here's kind of like, you know, just a look at a couple of the requests. Like, you know, you pull available updates. You say what version you're running. You get a response back, and it says upgrade to this version. And then in the second one there, you can see, you know, you submit your PIN. If you're familiar with like BlackBerry devices, like the concept of a PIN is consistent in Playbook world. And anyway, so you get like a list of packages you can download. So who cares? Basically, if I can control the version of software running on a device, I can do specific testing. You know, from a security perspective, if I know an organization has got a delayed, you know, upgrade process, you know, they have to put it through QA or whatever. You know, maybe it's interesting for me to go to a specific version. If I can extract the tablet OS file system without like, you know, gaining root access to a device, I can, you know, reverse engineer how some things work statically, diff changes between versions, etc., etc. So originally we could man in the middle of the system update process. Basically the X509 checks were not enforced. You actually just got a prompt if there was like a bad or like an untrusted certificate. So versions 101 and 103 for sure were vulnerable. I don't think that you can downgrade, but basically with this issue, if you buy a playbook and you man in the middle of it, you man in the middle it, you can basically control what version that playbook is going to be on. So that's interesting. And I believe, you know, if you can still buy a playbook at version 101, I believe that's probably what they still sell at. You know, you can still engage in this process. And obviously, you know, you get prompted, you know, accept the bad certificate. That's how it works. Before it was fixed. So this out of band bundle download, basically the process for that is in the request that you're submitting for an update bundle, you submit something, a header called X encryption ID, and it actually has some significance. It's based on the serial number of your playbook, and it is possible that some playbooks are available for like other, you know, certain updates. Like if you've got, you know, if you're internal and it's you know, a developer playbook or something. Right. Yeah. So you know, the actual like hardware identification of the device itself it's basically a hash, and it uses X encryption ID. I built this script to basically like pull and download updates out of band, and I found that you could actually do some brute forcing of unreleased versions. Here you see, you know, I basically like ask for firmware version 1093001, and actually get a response back, and it like shows me, you know, the URL to download that. Unfortunately, I can't download it because I don't have the, you know, the correct hardware identification, but it's interesting to, you know, that exists. That version actually, 109, that was never released, so I don't know what it was. Anyways, firmware reversing. Basically, to do this, we like use this out-of-band process to download a firmware image. It was a bar package, which is basically just means like a jar. It's just a zip file. We extracted that and got this like large binary glob thing. Maybe it was raw partitions. Maybe we can carve it up and just, you know, mount partitions. Had some interesting headers, MFCQ, QCFP. Didn't really know what that meant. Taking a look at the QNX SDP, sort of this like development platform, we were able to examine what QNX partitions look like. You know, basically, you know, building partitions and loading them up in a hex editor, and you know, getting some magic bytes. And that's EB109000 is actually the magic bytes for a QNX partition. So I actually just like searched through the firmware update, and sure enough, there was like 4 occurrences of that sequence of magic bytes. Okay, so they're valid partitions. Can we carve them out? What size? You know, how big? Just like using DD to kind of like hit those boundaries, you know, sequentially 1 to 1 to 1, they wouldn't mount. So something was wrong there. So going back to like the QNX SDP, they had some utilities for like examining like different artifacts from partitions, and through that process, it was this tool called check QNX 6FS, and basically like doing that, like I was able to, you know, sort of figure out like what some of these byte values meant, and specifically what was interesting is like the length. And as it turned out, like the length that was advertised in the superblock was bigger than the firmware image. So like, you know, clearly there was compression or something going on. On the playbook itself, there was a couple tools, QCFM, QCFP, that kind of like matched up with some artifacts that showed up in this firmware image. So just looking at these tools, you know, it kind of looked like something that might be relevant. So running that, running the tools on a partition, like a partition image, we actually got these, you know, some numbers that kind of like 2 sets of numbers that kind of like looked interesting. Like looking at the output of this application and then looking at, you know, the header of the output, like it turned out that it was like basically offsets, offsets of where something existed and where it needed to be. What was basically going on here is that it was just the process of like building a firmware image basically just like took out like blank space. So we're compressing by removing null space and then just like recording where those offsets need to be, which was pretty interesting. Going back to the actual thing, it's got all the right headers. Too long didn't read. It's basically like this envelope, this QCFM envelope. I basically just like built a script to go through and like parse those out and like insert null space. And sure enough, we were able to produce these 5 images. I'm on the projector. Okay. These 5 images, some of which were, actually like system partitions that we could mount. Another was this IFS image. It's like a boot image. There was like an SDP utility to mount that and pull files out of it. Sure enough, I even built a slide for it. The utility is called dump IFS on the QNX SDP. But anyways, it was pretty interesting. Based on this like firmware reversing, we could pull out all the scripts and binaries and stuff, and kind of dig into that stuff.
So I mentioned earlier that persistent publish subscribe system. So file system permissions and POSIX ACLs and group ownership and UID and user ownership of files and directories, etc., prevented apps users and subsequently the apps those users run as from reading and writing arbitrary things on the file system, things within PPS. There was and kind of still is this a unique file within PPS /PPS called .all. There are a few other special files, but .all. So as we see here, I think I have okay. So as we see here, I'm in /PPS/system. There's a file called bookmarks. The permissions on that file are only readable and writable by root and NTO. If we run git fackle, we see that same that expected output, and then another explicit entry for NTO to read-write, which is kind of weird, but it's there. So then what this represented was just the bookmarks of your browser. Anyway, so this .all file would actually aggregate the contents of all the other files in that directory, all of its siblings. So if you had a file like bookmarks that, as an unprivileged user, was not readable, through .all you could effectively read the contents of that file. Just a quick note, this is, because I know Rim's going to yell at me for this, this has since been fixed. .all still exists, but that leak no longer happens, and I'll explain why a little bit later. But this was in 2.0. So prior to 2.0, if you look, cat bookmarks permission denied, cat.all. I see the contents of the bookmarks file as represented by @bookmarks, as well as so the URL and when the user actually last accessed that URL. So, interesting slight bit of information leak. Another example in /PPS/services/networking. Catting.all there, we would be able to see all the nearby APs, Wi-Fi APs, which could, if you wanted to, then go and compare it to Skyhook or something and try to get a user's location without ever having to actually request like the read geolocation permission, because you could just read this file somewhat arbitrarily. Another thing, /PPS/system/NVRAM. This file device info, again not readable by us as an unprivileged user, but through .all it revealed the contents of device info, including the PIN. Another example, the video chat, which is you can call other playbook users. You could actually see through that .all leak when the user last talked to someone else, when they video chatted them, whether they made the call or the call was, if they received the call. So whatever, again, kind of been been fixed, but what we had found was, even though those examples were kind of goofy, they were just an indicator of like a really weird design decision with this whole .all thing, and a slight oversight as to what it might have revealed. So a slight deviation, and we'll pair this with the .all thing in a second. Native code. So when you write native apps in C or C++ for the playbook, as expected, you can have your app request a particular permission, like the ability to open network sockets would be the access internet permission. Our first proof of concept native app just requested 0 permissions, but was still able to, through this .all bug, read the device info contents and subsequently the device pin and other unique identifying information about the device. And secondly, also open up a socket, connect to just a remote listener out on the internet, and shuffle that data out. For a managed application, such as one written in Air or WebWorks, which is another runtime, this would have required, because there's a runtime managing that, this would have required that access internet permission and another permission called read device identifying information. But we were able to read stuff from the file system somewhat arbitrarily and send it out over a network socket. And this is my really horrible C code that does that. So there we see our remote netcat listener just receiving the contents of device and .all with the pin in it. So couple caveats with this. Currently, nothing really stops native code from opening sockets. So like the permission system, except when it applies to permissions that grant, or capabilities that grant file system permissions via authman. Those permissions are kind of moot. Like, you don't need to have access internet to open sockets. You can read to places on the file system that your app's UID has permission to do that without having some intermediary to enforce that. So what we did was just had another like really goofy example that just opened up a reverse shell in our app, our second POC. Calls this QNX function called spawnVE, which is sort of like handles all the fork exec magic for you rather than having to think about parent and child process relationships. And then just opened up our shell, and we got a shell in our playbook. The one thing about this in 2.0 that we observed was when the so spawnVE, like the child spawns off of the parent. When the parent dies, so the user closes the app, the process would get orphaned and under most Unices get like reparented to init or something. There's some kind of watchdog we haven't identified yet that then goes through, looks for an orphan process and kills it off. And this takes like 5 seconds to happen. So just a weird behavior. So the user before 2.0 would close the app, our shell stayed active. Now we have a window of about 5 seconds before that happens. All right, so back to why this is somewhat significant, or was significant before the .all fix. So Bridge allows you to, and I quoted, connect your BlackBerry PlayBook tablet to your smartphone to access email calendars or other data directly from your tablet. We interpreted this as where the good stuff is at, because that's where all the corporate data is. It turns out that all the Bridge apps, even though they have kind of a native playbook app look and feel, they're really just instances of WebKit. They're just single-site browsers that connect back to Sapphire Proxy, listening on localhost. Sapphire Proxy is this HTTP service that just facilitates talking to the handset, the paired handset over Bluetooth, and talking to the service, the Bridge service on there, which then reads in contacts data, email data, whatever, and spits it back out the other end to these Bridge apps as HTML and JavaScript. So they're just single-site browsers. So if you look here real quick, this is another entry that was in /pps/system/sapphire.all, and just had information about the Bluetooth MAC address for the current paired handset, the name of it, what the state was, etc. So the process for this is I open up the app on my tablet. It authenticates to Sapphire Proxy. If the handset has a password on it, I'll be prompted to put that password in. There's just a There's just a post to /auth/login on Sapphire Proxy. It posts some form data with name equals password, and then the value of my password that's set on the paired handset. And then I get an XML response that contains this thing called like this element login token. This key thing actually didn't seem to really matter too much for this purposes of this. And then each subsequent request by the Bridge app on the tablet would be something like get/contact/push some ID, a custom header called Sapphire token with that value, and then also that same value as a cookie. So it's web app 101. Like you authenticate to a thing, and then afterwards you keep using that same cookie, right? So it turns out through this .all leak, once the user had paired and set up Bridge and had unlocked Bridge, this token on the playbook side for the Sapphire proxy side had to be stored somewhere so it could be validated with each subsequent request. So it turns out, because of this .all leak, /pps/system/sapphire./.all revealed the authentication token. So kind of pairing this with the ability to have a native app that can read files in the .all file in PPS and also open network sockets, it goes that you could snarf this out and then just reconstruct the HTTP request that the Bridge app would do, connect back to Sapphire proxy, start pulling out email from the handset, and then open a socket and exfiltrate it somewhere. So we just kind of like gave a quick little curl example of this. So here we just have me zooming in on the thing I shouldn't have zoomed in on yet. Curl, sends the header of Sapphire token, that token we saw earlier. Also sends it as a cookie, connects to localhost, TCP 187, where Sapphire proxy is listening, passes in the URL for a particular message ID, and then the response we get is valid. We see email here. So combine that with your native app that doesn't have permissions enforcement, and there you go. There's some redacted email. So RIM gave us a CVSS of 3.6. So we were, that's pretty low. We had an interesting discussion about CVSS after that. So I'll just leave it at that. But the response was good, and we're all friends. Yeah, so the .all info leak was fixed in 2.0. And what it does now is, too long didn't read, you can still read .all, but it will only show you the contents of other PPS files you would have had read access to anyway. So there's just an additional perm check. Hi, Kim. So as it turns out, Sapphire proxy also acts as an open HTTP proxy. So all the traffic that goes out over Sapphire proxy goes over that Bluetooth link and back out of any network, the Wi-Fi radio or cell radio of any network that the paired handset is connected to. So if it was on your corporate Wi-Fi network or had a VPN back into your corporate network, you could then pivot from your tablet over to whatever that had access to. So this might include BES or BIS servers as well.
Cool. So we're running a little short on time, so I'll kind of fly through this. A couple of words on App World. It's basically like the App Store for BlackBerry stuff. It's the same for PlayBook and BlackBerry OS handsets. Basically, in the process of man-in-the-middling stuff, we took a quick look at this. There's an asynchronous application purchase and download process. Like, you purchase a thing and it's secure, and you're given an HTTP download to download your package. So, taking that as a fact, consider the following requests. These are two. The purchase process has happened. These are the two download requests to get the actual package to install. It's a GET request. We've got a number, custom user agent. In the second one, it's another number. It looks a little similar. Yeah, sure enough, those file names are sequential, and there's no session management on that. So you can actually download all of AppWorld. And there's a humorous, it's intended to be humorous, this little tidbit of bash shell at the bottom here. To go from 0 to 8 million would actually take you a really long time, but it would work. Basically, you can just download the applications. Angry Apes, you can download this and save yourself the $2. That's actually the actual package name. You could just download that. But anyways, what's kind of interesting about AppWorld is it seems to host all versions of all applications. So instead of like a package having a number and it always living at that, you know, having that URL, as new versions of the applications come out, you know, they just like sort of put it on the web server or whatever. So there's like some application archaeology to be had there probably. Another interesting thing, there's no centralized license management, so there's really not a way to keep you from downloading these things and installing them. Not unique to PlayBook, it's also significant for BlackBerry OS, same thing with the applications. And the response on this one was actually, you know, I downloaded like 120 gigs worth of applications, and then our office IP got blacklisted, so whatever. A couple words on just like web services. We mentioned that there's a web server that runs on this device. You know, all the stuff that you see right here, like all these like CGI scripts, like all sort of like external access is sort of like goes through these web requests, which is kind of strange, we thought. You know, there's a login point. You know, you log in, provide your credentials, and you get this DTM auth token, and that's basically like your access to the device. That's like the session. You know, could we abuse that? Maybe, but you know, it's a little bit impractical because of PF rules. Like we can't directly access this web service from the device. But as it turns out, we actually could do something with it.
And also, just for clarification, DTM auth is like DTM meaning like desktop manager. So that's in case you were wondering what that meant.
Sure. So actually, you know, when this was still valid before the .all fix, we could actually use both the bridge proxy and this token, which we could, you know, which we could read out. It was just another PPS object, and we could actually just like basically issue a curl request like from the playbook itself to install an application. So like we could install arbitrary applications.
But note that it had to go over a bridge out to the paired handset and then back to the playbook. So it's kind of like this really roundabout way of getting back access to the service we didn't have access to.
Sure. And again, we're running a little bit short on time here, so I'm just kind of fly through this stuff. You can see there it's successfully installed, so that was pretty interesting. Just a couple additional considerations here. Just so you know, we have a few slides here. Samba is running on this device. There's actually like RIM had like a security fix. It was like there's like a Samba vulnerability, like in, you know, just like generic Samba, was patched, but it was like a critical vulnerability. That was just recent. Basically, it's used to any of like the file sharing between like your PC and the device is using Samba. It's either Wi-Fi or USB. It's pretty interesting. If you would actually, I have on the bottom here, pro tip: leave file sharing disabled. Like, if you know, if you don't have a password and you turn on file sharing over Wi-Fi, like anybody on your Wi-Fi network can just like, you know, get at your files. So. Another thing to consider, Sapphire proxy. So we kind of like, it was kind of interesting in the context of like reading emails. This is from one of the startup scripts. You can see it actually defines a, what's that, laser? Sure, it actually defines something, a variable called bez address, and it's on a different port than what we were accessing. And if we look at the description, you know, I just ran strings in the binary, and this is the description. It actually like points out that like this is intranet access. Like this is proxying through intranet access. That's protected with through PF. Like so, apps shouldn't have access to that. But you know, with a privilege escalation, if you can raise your user ID to root, like you could potentially proxy into an intranet from the service, which is, I think it's interesting. You want to just like...
Yeah. So one other thing, the bridge files, the things that are on the handset, the paired handset, are exposed to the playbook over WebDAV, so it uses kind of like a user space file system to mount this WebDAV export to /BlackBerry on the playbook file system. And that includes like internal storage, SD card, images that are on there. File system permissions are controlled through, so you'll see like here, it's not world readable, but the GID 1000, which is called, maps back to a name of 1000 shared. That actually, that's a case where even a native app permission actually has significance. So access underscored shared app perm will give, at runtime, an application with that permission group membership in this GID 1000, group 1000, and subsequently be able to access most of what's in /BlackBerry and subsequently what's on the paired handset. So just kind of interesting, you know. So and since some of those, like the SD card file system is fat, some of the permission concepts don't apply here. File system permissions concepts. That included from the paired handset app world log. So using app world on the handset, some of the user behavior and activity got logged there. So anyway, even though the .all thing was fixed, it does kind of raise the bar a little bit and make things like PrivEsks a little more valuable, because now you have to actually, you know, own the device to really own the things it talks to. So these issues may resurface. Some other things to just keep an eye on: a lot of the system scripts are a bunch of questionably glued together Python and shell. Android support now in 2.0. That's an area like we're kind of, you know, interested in looking at, and you might be as well, because there's a lot of kludgy stuff in there as to how the Android environment's set up, since Android runtime was kind of shoehorned in there. What future issues with file permissions, like the .all thing, for instance, might be interesting as well. Support apps, so desktop manager and device manager, you know, owning one of those might be interesting. If those have bugs, could that let you pivot onto the handset or the tablet itself? So anyway, we're completely out of time, so sorry if we had to rush through a few things. But if you have any questions, there's our email addresses, our Twitters, and where all the playbook tools that were written are published on GitHub. And we're supposed to tell you to fill out the survey as well. So sorry for rushing a little bit, but thanks for coming to the talk, and if you want to catch us outside of here, you can too.